really the magnetic field. Did you all get a chance to take a look what I posted? Did anybody? You did, good. Did you have any questions?
Not really.
All right, I mean, a lot of this is the physics you've had before. It's basic magnetic stuff, but unless you review it and stuff, you can really fall prey to, I guess, an overconfidence, and you start really making stupid mistakes. Now, a lot of this parallels stuff we did in electrostatics. I want to finish the thing with the loop, then we'll go to the wire and stuff like this. But remember this, in general, when you have a current IBL, this is just a current element, and you want the differential magnetic field, we call this R, and R is going to be a vector measured from the source of the magnetic field, the point of observation. Here, the differential magnetic field is IBL crossed into AR over 4 pi R squared. Now, AR is a unit vector. In Whitworth's book, he'll say AR 1 to 2. It's really always from the source of the magnetic field to the point of observation of it. So that's it. Now, if we have a loop, last time I was doing this, do y'all remember I was starting this? I was trying to finish it. If we have a loop right here, and this is in his book, it's, I think, one of the earlier problems that he shows you. It's a classic problem. We have a loop of a radius A, call this X, Y, and Z, and you want to know the actual H field here at a height Z above the plane. What you always do is start with a differential H field from a differential amount of current on the loop, and then you write the equations and just go through the process of evaluating each step and finally doing the integration. That's the only thing you end up doing. So if I say I have a differential current here, IDL, differential chunk, this is vector R, and here's my observation point. And I would have a differential H field here. We'll do this. I want to just go through it one time completely. This is the same process you'd use for any type of a current distribution. Find the differential H field from, then do the total integral, and find the complete H field. By the way, do you see how this parallels the stuff in electrostatics? We find the differential E field from a differential charge. Then you integrate the differential field over where the charge exists to find the total E field. Same deal here. Now, and then you got to make sure you see this. For R, vector R, that's always measured from this point to this point. So it's going to be in terms of the radial distance. What's the radial distance of the point of observation, class? Can you all see that? It's 0, right? It's on the z-axis. The radius is 0. Do you all follow me? All right, so it's going to be 0 minus whatever this radius is. I'll call it A. So it's going to be minus A, right? And, I'm sorry, the point here is 0, and here it's A, so 0 minus A is minus A rho. What about Z? Point here is at Z, right? And point here, 0, correct, class? So it's just going to be plus Z, AZ. That means, and I'll do it this way for this one, the magnitude of R is simply going to be square root of A squared plus Z squared. Everybody follow me on that? Then if I want a unit vector, AR, that's always going to be R vector over magnitude of R. That's always going to be the way a unit vector is determined. So that's simply going to be equal to minus A rho plus Z AZ over square root of A squared plus Z squared. Next thing I'm going to do is find IDL, and I'll put it right here. So what is IDL? Does anybody remember from last time? Well, I is the magnitude. It's going to be a scalar value. You all with me? What is DL if I'm on the rim here? We're in cylindrical coordinates. Does anybody remember? It's going to be the radial distance d phi. Do you all follow me? So it's the wiper arm length. I always think of windshield wipers. Wiper arm length times the differential actual angle. So it's going to be A d phi. In what direction, class? A phi, correct? It's in the phi direction. How many see this right here? Did you guys just go down with a test or something? No? Nobody did this stuff, really?
Long homework.
For who?
Homework.
Yes.
For me?
From a different class.
Oh, never mind. Y'all with me, class? On this one? Now, pay attention. I know you get, it's very easy to say, oh, I got this. But there are, I promise you on a test and quizzes, people will have major, like just, I guess, the brain freeze or something. They don't see the next logical step. If you do them, you will, but you have to force yourself to do them. So now I put it all together and I get DH here is equal to what? Well, it's I, right? DL, which is A, D phi, A phi. Y'all follow me on that? That's what DL is in this one. It's crossed into the unit vector. Let me get to that in a second, but I'm going to put the 4 pi. Now, R squared is simply A squared plus E squared. Do you all follow me on that? If magnitude R is square root of that, R squared will be equal to A squared plus E squared. Is everybody good with that? So I'm going to put just A squared plus Z squared. Now I'm going to put the unit vector here. Minus A rho, and then it's going to be plus ZAZ. But I have to divide it by this square root, so that makes this to the 3/2 power. Make sure you can see every step I've done there. The square root term will make the A squared plus E squared go to the 3/2 power. How many see this? Make sure, if you don't, I'll clarify. Y'all with me on this? All right, now, we do the cross product, and I'll put this up here. You have to know your cross products. So in general, if you have X crossed Y crossed Z, or go this way, they're all positive. That's the way I show it. If you go in the opposite direction, it's negative. Do you all remember seeing something like this in math, in your math classes? How many do? You know, everybody did cross products, right? You had to be in here. All right, what about if you have rho phi z, this way it's all positive. If it's the other way, it's negative. You all with me? I'm just putting this there as, it helps sometimes if you don't do this all the time. So when I do this, I find out that DH here is going to be I times A over 4 pi A squared plus Z squared to the 3/2 power. And now I'm going to take, I'll even put the D phi out in front. Now when I have A rho crossed, A phi crossed A rho, I get what? Can you see it over there? What is it? Isn't it minus AZ, class? Take a look. So with that minus sign makes it plus. So it's AZ right here. And then when I have A phi crossed AZ, what do you get? Can you all see it or not? What is it? A rho, isn't it, class? All right, it's going to be plus ZA rho. Now that's technically the differential H phi. I want to make mention of something. Y'all see what I've done. You'll notice that there's an A rho term right here. Now, if we go ahead and take the next step, which would be to integrate around that loop where D phi exists, then you would find is this. I'm going to do it. You're going to have H equal the integral of that. Now, you can see the A squared and Z squared does not depend on phi. So it's really these two things. I'm going to rewrite this because I want you to see this. All right, this is what it would be if I put the integrals in the order they came. You'll notice this integral right here just brings out 2 pi. It's 2 pi a. Can you all see this? Now for this integral, this is the bad one. If you look at this, your gut says, well, it's just 2 pi a rho. Do y'all follow me? But a rho is a function of phi. Now, I'm going to tell you why. In general, when you talk about a rho, it's a unit vector, right? That is going to have, it's going to be at some angle, some phi. Y'all follow me? When we do this d phi integration, technically a rho, I'm going to write it here. He doesn't do this in the book. Is really going to be equal to ax times cosine of phi plus ay sine of phi. Now, if you think about this, I'll try to show you this. If this is x, this is y, and here's a circle of radius 1, this would be a rho, right? The projection on the x-axis would be ax cosine of phi. The projection on the y-axis would be ay sine of phi. Can you all follow me on that, at least? How many see this right here? Now, if I go ahead and I put in for a rho, ax cosine of phi and ay sine of phi, and I integrate from 0 to 2 pi, the sine or cosine, what do you always get when you integrate sine or cosine from 0 to 2 pi? 0, right? Anytime you integrate a cosine or a sine wave over an entire period, you get 0. Remember that. All right? It always is going to be the case. That's the reason this term is of no consequence. It goes away. Now, in Dr. Wentworth's book, he says an argument of symmetry. Now, what he says is this. If I take a look at this, anytime I have a differential current here giving rise to a differential H field, there will be an H field that will have a horizontal component to it. Y'all follow me from here? If you go to the conjugate point right through the center here, you're going to have another DI, or really IDL really, and it will give rise to the same exact H field's magnitude in the Z direction, but in the horizontal direction, it'll be at a 180-degree difference and it'll cancel. That's his argument. Y'all follow me in that class? So he makes the argument it just cancels by symmetry, by inspection. In either case, it's gone. This is the only thing that exists. Now, when you get that, your final H field from this one, this is in the book. This is going to be 2 pi, right, times A. There's a 4 pi, so it becomes I a squared over 2 a squared plus z squared to the 3/2 power, and it will be in the AZ direction. The units of this are going to be amps per meter. I get out of your way. And that's the H field from a single loop. Got a question for you. What does your instinct tell you would be the case of the H field if I had 2 loops on top of each other? I had shellacked wire and they were separated by almost no distance. What do you think the H field would be for 2 loops of wire? Anybody? Twice that, right? Now, that's true for 2 or 3 narrowly stacked, but if it's a solenoid, it's a little different. We'll get to a solenoid. You know, a solenoid has hundreds of turns of wire over a given length, right? We'll get to that in a bit. But this is really the H field from an infinite, or from a finite loop of current, centered in the XY plane. Can you tell me where it is in the book? Anyone? What page? I'm trying to give you this so you can put markers on your book pages and you know where it is. It's in the book. I just don't know the page. Anyone? Quiet class today.
I think 216.
216? Okay. Everybody with me on that? All right, next we're going to do the infinite loop. You have to know this one, by the way. And you know, what does this look like? Do you remember when we had a loop of charge? Right? A simple wire of constant charge density. Do you remember what the E field was? Or D field? And it was a very similar form to this, right? There's one difference. That has the actual A squared on top, right? And by the way, I didn't say this one, but if you take a look at this form right here, just look at it for a second. Where is the H field a maximum? I want you to just look at it as a function of Z. Where is it a maximum? At Z equals 0, right? And if Z equals 0, what is the magnitude of the H field? Well, downstairs I would have A cubed, wouldn't I? Because the 3/2 and square power would just give me a cube. A cubed, A squared would be I over 2A. That would be the peak magnitude. Y'all follow me on that, class? Now, if we had a loop of charge, the E field at the origin will be 0. And the reason is because there's the height Z that'll weigh. I'll talk about that later, but these things directly compare to each other. And I'll try to draw this stuff up. I'll contrast all this when I'm done with the the current distribution. So this is for a single loop. Next, if we have a straight wire, and this one, see, I don't actually know how many of you remember this stuff from physics, where they go through these, they're called canonical problems. How many remember this loop problem in physics? Really? This is a classic problem. Almost all physics books have this that I know of. Next, we're going to do the infinite wire. It could be finite. Problems I gave you, one of them is a finite wire. So if we have a current on the z-axis, we're going to assume the z-axis has a current I on it. And we want to know what the H field is, say in the xy plane, at we can just call this distance rho because it would be radians. And we want to know what the H field is. That's our goal. So, and it's a classic problem. The way you go about it is, remember I put it up here, the differential H field is equal to I dl crossed into AR over 4 pi r squared. And that's it. That's the differential H field. Now you just have to know what each of these terms mean. First, we have to say, where's our differential current? I'm going to put it right here at a height z. So I'm going to say this is at a height z above the xy plane. And this IDL will become I dz az. Does everybody follow me on that? I is the magnitude, dz is the direction, and az is the orientation. It's in the z direction. Everybody got that? Next, we need the radius vector. That's this vector here, r. Remember, it's from the point where the current is, the differential current, to the point of observation. So what would r be in this case, class? Anyway. Well, think about this. Start with the radial coordinates. Radial distance here is rho, right? Radial distance here is 0, right? You all follow? So it's rho, a rho. What about z? Radial distance here is, this is the point of observation, is 0. This is z, so 0 minus z is minus z. You all follow in that class? So it's minus z a z. And here's the way you always think of it. Just imagine yourself at this location. Which way is this vector actually pointing in the magnitude? Y'all with me, class? That's the only thing you have to do. So I've got r. What is the magnitude of r? Anybody? Square root of rho squared plus z squared. Agreed? I'm going through it blow by blow. What's the next thing I'm going to get? A r, right? Unit vector in the direction of propagation, or direction of orientation of this is going to be r vector over magnitude of r vector. Or it's going to be simply rho a rho minus z a z over square root of rho squared plus z squared. Correct, class? Now, I think I've got everything I need. Yeah. Now I can write dh. And when I write dh for this one, I'm going to get IDL or I dz az. And that's going to be crossed in my unit vector when that's going to be rho a rho minus z az. All this is over 4 pi. And then we're going to have rho squared plus z squared. Now normally it'd just be the first power, but because of this unit vector has the 1/2 on it, it becomes 3/2 power. The units would be amps per meter. Well, it's got a differential there, but it'll eventually be amps per meter. Do y'all follow me on this, class? Now do the crossing and make sure you do it right when you do this one. So to get the DH after the cross product, I'll take the values out in front that are scalar. I'll have I, 4 pi. And then when we go ahead and do this, we have AZ crossed A rho. What's Z crossed rho, class? A phi, right? So it's going to be rho A phi all over rho squared plus C squared to the 3/2 power. And then we have Z cross Z. What is Z cross Z? AZ cross AZ is 0. Do y'all know this, class? How many do? All right, hopefully you remember dot products, AX dot AX is 1, AY dot AY is 1, AZ dot AZ is 1. But if it's cross products, AX crossed AX is 0, right? AX crossed AY is AZ and so forth. Do y'all remember this, class? These are going to be very important that you know this by heart and you use it. All right, so the Z component goes away. Now I have this. And now technically, if that's DH to get the total H field, I have to integrate that over where the differential current, or really the current exists. Now, if you integrate it, if you just put a finite integral here and make it, just call this, just suppose the wire started here, and I'll call that Z1 and ended at some Z2 here. If it wasn't infinite, then you would put Z1 here and Z2 here. In other words, it would be over the extent. Do y'all follow me, class? And you do the integration. We could do this. This isn't that bad, but I need to put the dz here. I forgot that. There's a dz here. It's a differential in terms of z. This would be of the form of dx over a squared plus x squared to the 3/2 power. It's going to render something where you're going to get a 1 over rho squared plus e squared to the 1/2 power as a result of integration. Anyway, when we do this, if we let these two things go to infinity, by the way, this is a problem I gave you in the book, by the way, to do. Yes, sir?
Could you not take the rho A phi out?
Sure, you could. You could. As a matter of fact, I mean, you can take rho out because it's constant too, but I'm just showing, if you wanted the whole form of the integral, you could take rho out and put a phi here. And now you can see the form of this integration is 1 over a squared plus x squared dx up top. Y'all follow me? You can look. And that'll be, to the 3/2 power, that's going to be 1 over rho squared plus z squared to the 1/2 power, and there will be another term that comes on top. But if it is going from minus infinity to infinity, this becomes, and this is an important result that I'm going to contrast. This is going to be simply I over 2 pi rho in the a phi direction. This is the amps per meter. So this is real important. This is what it would be here if we integrate that to get the total H right here. It goes from minus infinity to infinity. That's in the book, but I don't know what equation it is. It's before the single loop. Do you know where that is?
It's 216.
Still on page 216?
Yeah, the other one was 218.
Oh, sorry. The other one was 218. 216, 218. They'll have both of these. They're classic things. I want to contrast this to what you know about the actual line charge. I should do the loop too, but right now I'm going to do line charge because you'll see it. All this stuff parallels electrostatics exactly. So if you had an electrostatic charge density here, suppose you just had infinite line charge on the z-axis, and you wanted to know the actual electric field at a distance rho away. Now we did this entire problem. How many remember doing that? We got a differential electric field from a differential charge, then we integrated over where the charge existed, and we found the E field was equal to what? rho L over 2 pi rho epsilon naught A rho. Y'all remember that? How many do? This has a constant epsilon naught. The H field doesn't. If it was the D field, we wouldn't have epsilon naught. It would be identical in form in terms of the 1 over 2 pi rho. There's a 1 over 2 pi rho there. That has I, this has rho L. That direction is A phi, this direction is A rho. Those are the differences. But you see the similarities. It's important you do. Okay. So now we've done the loop and an infinite wire. The next logical step is to use these two things as building blocks or as differentials for typical charge distributions. And he does this in his book. He starts and let's see, which one do we want to do first? This is in chapter 4. Let's see, we did that. I'm going to do this infinite sheet of charge next. It's on page 223. So here's the deal on this one. I'll try to show it to you. Suppose we have an infinite sheet of charge, or sorry, of current, pardon me. And we have a current all flowing, say, I don't know which way he has it going, but he's got it in the z direction. So he's calling this z direction. He's got all this current. Now, because it's a surface current at this point, it's not just a single wire of current. You have something called a surface current density. The symbol for that is K. So this is an infinite sheet of current. It's infinite in this dimension and that dimension. And K will have something where it's going to have a magnitude. You can just call it K0, but it'll have a direction, AZ. And the units of K are going to be amps per meter. It should make sense if you think about it. There's so many amps per meter. If you had a certain width, if you just took a width of this W, and you wanted to know the total current I flowing there, it would be W times K would give you the amount of current flowing over that width. Make sense to everyone in class? It's called a sheet of current or surface current. So we want to use that to calculate the actual H field above and below it. Now, I'm not good at perspective drawing, so I'm going to do it this way. I'm going to say, if this is the z-axis, and the sheet of current is, wait a second, does he say it's in the z direction? I think he does, right? Yeah, let me do it. I got to change up this orientation. If I assume that I'm looking, if you think about if, let's see, x, y, z, all right, if this was x and this was y, then z would be into the board, and you would have basically, the current would be going into the board everywhere here. I'm just trying to show you, I've taken this and I've flattened it out so we're looking down its axis. This is into the board. You all follow me on this class? It's infinite in its extent. It's here. I've got a sheet of current, right? Just try to imagine this. What I'm going to do is this. I'm going to say, if I just looked at a sheet of current of a width, I think, yeah, we can do this. I'm sorry, this is X, this is Z. So if we talk about this and it has a width delta X, then the total amount of current in here, or delta I, would be equal to delta X times K. It should make sense to you, right? Sheet of current, amps per meter times delta X meters. That would be that would be the amount of current. So what this looks like is actually a single wire of current right there. As a matter of fact, I'll try to draw it over here so you can get a clear idea of what I want. So if this, and I'm going to use this to see one thing about this. Yeah, he wants it on the y-axis. So if this is the y-axis right here, just follow. If I have a certain amount of current I right here, and it's displaced by this distance z, and I gotta make sure, I'm trying to stay consistent with his book. Yeah, this will work. So I'm just saying I have this amount of current at a distance z away. Follow me? Or I can actually say at minus z here, and I want to know what the H field is right here. This is an important one, by the way. So this is going to be radius vector r right here, and now I want to know what the H field is. Let me say this current's going in, so I want to know what dH is. Now, what I'm about to show you, I don't want to confuse you on this, so I'm going to try to be as clear as possible. Just listen. You know, if you have an infinite wire on the z-axis, and I'll put it here, we just found out if you have I here and your distance rho away, the H field right here, total H field, if it's infinite, would be I over 2 pi rho A phi. Y'all follow me on that? Now here's the thing he's not stating real explicitly in his book, though he does show it. First of all, rho here would be a vector. This rho actually is a vector. And from that, you get A phi here, and that's really equal to AI crossed into A rho. I'm going to explain that in a second. AI is a unit vector in the direction of the current. A rho is a unit vector in the direction of that radius distance. Do y'all follow me? Or the radial vector. So for this one, if we looked at what A phi would be, AI would be in the AZ direction for this one. I'm talking about this as the classic problem. And it's crossed into A rho. Well, for this one, A rho is A rho. You get 0, you do get A phi. Y'all follow me, class? I'm just showing you. Now, look at this one. It's a little different. Here, my vector R there would become my radial vector rho. This is important. Y'all with me? And it's pointing from here, from the source of the infinite current line to the point of observation would be A rho of the H. Y'all with me? Now, what we're going to do is this. We're going to say if we had a current, and this would actually be DI, if we had a current I here, and we wanted to know the H field there, we would simply use this equation, I over 2 pi rho A phi, and rho here would be the distance from that point to the point of observation, which would be, I guess, z squared plus y squared square root. Y'all follow me? If you look at this, because it's up a distance y. But now if we have differentials, it's a little different. I'm going to say, instead of a total H field, I have a differential H field. And that's equal to the differential current, which is K dz. And this has a vector, and it's over 2 pi rho. Actually, you can make it a scalar if you want on this one, because the vector sense we're going to take with A phi. Now, A phi on this one becomes equal to, and here my vector rho, this is where it gets confusing. I want you to just watch this now. This is how we get the A phi that will go in this equation and in that equation. Here, rho is actually going to be, well, that's at a height y, so it's y minus the y here is 0, which is going to be y ay, and for z, the z here is 0, this is minus z, so it's going to be plus z az. Ax has no meaning on this one, because it's an infinite in that extent. Y'all with me, class? Now, go ahead and do the math on this one. That means the actual vector rho here is going, the magnitude of rho is going to be square root of y squared plus z squared, right? And then to get A phi, or better do this. Here, what I have it is AI, a unit vector in the direction that the current's going is AZ. It's in the AZ direction. That's on page 2, what? What page are you on right there? That's it. 223 in your books, if you look there, if you want a good visual. Page 223. This is AZ, that's the differential current is AZ. We have a rho here. A rho is going to be simply YA1 plus ZAZ over the square root of all that, square root of y squared plus z squared. So I have a rho, and now to get a phi, I'll do it here. A phi is going to be equal to AI crossed into a rho. And that's going to be AZ crossed into a rho, which is all that stuff, which is going to be YA1 plus ZAZ all over y squared plus z squared 1/2 power. And here you can see what happens. I have z crossed into y is minus ax. It's going to be minus y8x. And then z crossed into z is 0 over square root of y squared plus z squared, which would be a phi. Then you're going to come over here and I'm going to do this right now. Now to get the total H field, I say first the H is going to be equal to K dz over 2 pi, and then I have rho. And that's going to be and this too, so it's going to be y squared plus z squared. And on top, I'm going to have the value minus y kx. And I've got to integrate that. Should use, wait a second.
Why are you crossing?
Well, you have to have AI crossed a rho. Give me 1 second here. In his book, I'll show you where this is. Oh. I'm sorry about this. I made a mistake on one thing here. Let me try to draw this a little better. I made one mistake. What I'm trying to show you is, and I'll do it this way, I think you'll see it better. So if this is the z-axis this way, and this is y, and this is x, we're having an infinite sheet like this in this direction. So if I have a current here, this is my problem. If you have a current right here, a differential current, it's going to be really k dzy, or I'm sorry, k dxy. My bad, this is k dxy, not dzy. In this direction, and I talk about a unit vector here, rho, that's going to be y, ay, and then it's going to be minus x8x, because this is going to be at a position x, and I could call it, if this is, it's going to be minus x, ax here to this position. This is what this is. So when I do my cross product, this should be actually minus XAX. And that means this is going to be and this is going to be x squared. And then here, you're going to have z cross y is ax, y, ax, and then you're going to have z crossed, and z crossed ax is minus, so it'll be plus x a y. And then this is the differential formula. I'll tell you what happens. When you do this integration, you find the h field. And this would be over the limit of, this is actually dx integration right here. So this is dx right there. And you go from minus infinity to infinity. You're going to find the h field is simply going to be k over 2, and it will be in a direction that's going to be equal to AK cross A normal. I'm going to talk about this in 1 second so I can finish this and make it clear. This is in his book. He shows you this on equation or problem on pages 223 and 224. But here's what really is going to happen. Follow me on this. This is going to be equal to h itself will be just exactly equal to k, and that's just going to be the magnitude. It's really, you can do it this way, k cross a. You can take k vector crossed into a normal vector over 2, and that would be amps per meter. Now, I want to try to make this clear to you because this perspective drawing might be a little tough to understand. So hang on, I'll try to make it clear. And I think you'll see it. Now, I'm going to tell you a trick with something called the right interval. If you have a surface current like so going into the board, all right, so assume this current's going into the board, it's in surface current K. As such, the magnitude of the H field above or below will just be K over 2. That's the magnitude. And the way you get the direction is this. Take your right hand, put your thumb in the direction of the actual current H. Your fingers point in the direction of the H field. So if this, say if this is this thing's in the Z direction, all right, if this is the x-axis here, y-axis here, if you're above here, just watch this. I'm saying this is the x-axis right here, going that way. If you're above it, the H field's positive AX. The value here will be equal to, you just can put magnitude of K over 2 AX, amps per meter. It would be in this direction. If you're below it, right, your fingers point in this direction. Can you all see that? If you're below it, so the H field, same magnitude, magnitude of K over 2, but it would be minus AX, amps per meter. And that's it for an infinite sheet of current. How many remember if you had an infinite sheet of charge? The E field was what? It was rho s over 2 epsilon naught magnitude, right? And it always pointed away from the actual surface of the charge. Do you remember that? If you're above it, positive z, below it, negative z, if it's in the xy plane. I'm going to at least remember that, right? It's this here, it's very similar. The magnitude doesn't matter how far away you are from the plane. To get the direction, if you're above it, it's going that way. Basically, just take your fingers, your thumb pointing in the direction of current. You're below it, it's going the opposite way. And likewise, if the current was coming out of the board, then the H field above it would be going that way, the H field below it would be going the opposite direction. Here's where this is useful, by the way. A lot of these things seem so abstract, like why are we talking about it? When you deal with real problems in the real world, and I had to do this, like when lightning strikes something, it causes current to flow. And on the surface of, this was a multiple launch rocket system we did this on, when you're close to the strike point and you're talking about metal surfaces where the current pretty much will spread out uniformly, we know there's a current I coming down and it's spread out over, say, just a flat beam or something like that. We can take I over the actual width of that beam to get the surface current density. And if you're talking about measuring it right at the surface, you can assume pretty much it's an infinite plane. And it's very accurate to do this. And we could get the actual estimate of the current density from B-dot probes we had. And from that, we could estimate the actual current that struck, the target current. And it was verified. It did match. But these are things that you would use in the real world if you were doing some sort of an analysis of measurements. You use them all the time. And sometimes for design, but basically analysis. These are really handy tools to use, these formulas. So that is from an infinite sheet of current. Now, the next thing is the toroid problem. This is on page 221. And I'm going to tell you, we'll do this one. Try to finish on a high note here. And again, I'm going to give you problems. Please do the problems. Friday, you're getting a quiz on this stuff, so please make sure you do the problems, do them all. You know how to do them. Isn't there a Friday quiz, right? Okay, I just announced it again, but yeah. Quiz Friday on this. We have it every Friday usually. Okay, so. So here's the next thing. We're going to assume we have a solenoid. Now, a solenoid is just like a hollow tube with a constant amount of, you can think of it this way, just a long tube with a whole bunch of turns. Matter of fact, probably like this. If you had something like this, you got a whole bunch of turns of wire around it. And the way they usually do this, they say they have a height h, and they have n turns of wire. And then they have a current I. Then you can put I in any direction you want, but you can have I here. What their goal is to find the H field on the axis of that solenoid. Now this is solenoid, it's useful to know this. As a matter of fact, you can use this, something like this, to make something called a coil gun and fire metal projectiles at this thing. I've actually helped the guy build one of these. One time it shocked me. That thing could fire nails. But nevertheless, when you do this, how do you think you do this, by the way? I've got all these turns, they're tightly wound, they've got a current I, and I want the H field. Assume this thing is on the Z-axis, it's got a radius of A, all right? And say this is the origin, say it's centered about the origin. Here's X, here's Y. And now if I'm at a height Z above it, and I want to know the H field, how would you get it? Just think to yourself. It's not hard. You always start with a differential approach, don't you, class? So I know the H field from a single loop. I just did this, we just did this, right? If you have a single loop of wire in the XY plane of radius A, and you're at a height Z, the actual H field from this would be equal to I, A squared over 2, A squared plus Z squared to the 3/2 power, and it would be in the AZ direction. Now we just did that one. If you don't remember exactly, you can look back, but you all understand this. We have this, right? So instead of getting, this is for a current I, what if I have a differential current, say here, this isn't being drawn very well, or better yet here, say I have a differential current here, all right, and call that DI. Now that's in a loop form. Do you all agree with that? that differential current can be defined as simply what? Well, if you have a total current of Ni, would be the total current going around there, right? If you divide that by L, wouldn't that be the differential current, right? In terms of amps per meters? Each turn around there causes an additional I to flow, right? So you have Ni total current flowing around a solenoid. It's over a length L. This would be the amps per meter. Then if you multiply this by dz, that would be di. How many give me that? That would be the differential amount of current for a segment of a certain thickness, dz. Y'all follow me, class? Now, if you take that and you say, well, that's the differential current right here, it would cause a differential H field. The distance difference here has to be z. So I can say, and I am out of time now. Tell you what, I'll finish this up. This is in the book on page 221. I'm going to give you a bunch of problems. Please do them. The quiz is based on this homework and the past homework. All right. Well, the past homework that a lot of you didn't do. Please do it. And it's going to be something we're going to have to calculate the magnetic field from some kind of a structure current. Okay.
Yeah.
I hope I feel better about that. Dehydrated, tired.